So, I suppose a lot of you will be familiar with the existing dynamic forms that we've got in test creation. And you're probably wondering, what's the difference between what we've already got and what we've called External Optimiser. So that's our implementation of using the linear optimizer to generate lists. So Dave did talk briefly about it, but I'll just talk in a little bit more detail about why you would want to move across and what the differences are. So the key difference is about the way the items are picked in our dynamic rules. So in dynamic rules, it goes through sequentially. So it picks items for rule 1, puts those in a pile, then takes next rule, selects items for that, puts them in the pile, and just carries on through. So that means if you've got rule 1 says, give me 5 red items, there's nothing to stop rule 2 picking some more red items. So they're not sort of hard constraints on the maximum values for your numbers of items. Whereas in the External Optimiser, if you define a rule that says I need 5 red items in the section, there will be 5 red items in the whole of that section, and that rule can't be broken. So it's not that one way is wrong and right, it's just a slightly different way of defining the rules for the exam. It does mean you can't directly port across rules that have been made in dynamic into External Optimiser, although that's not to say that some can't. So the next thing, which is another important difference, is that you can define psychometric constraints on the new External Optimiser test. So that's item response theory. You can define a test information function. So I'm sure some people who probably won't know what that is, but I'll talk a bit more about that later. But basically, it's just a representation of what level of ability of candidate the test is designed to test. So it tells you how hard the exam is. The psychometricians, people like Leanne and her team would define the test information function, the TIF, and then you can also define the tolerance on that. So we say, this is what we're aiming for, but we're willing to compromise above or below that by a certain amount. Then the third difference is that the External Optimiser, individual lists are generated dependent on previous lists. So in the existing dynamic rules, each list is generated completely independently. What's been generated in the past has no effect on what's generated in future. So it doesn't do anything to control the exposure of your items. Whereas in External Optimiser, we're feeding back the data from the usage. So if item A has been used lots of times in the previous lists, then it's less likely to be picked later on. And the idea of that is to try to even out the exposure, like we just looked at with on Leanne's slides. We've also built in better handling of friends and enemies. So we talked a bit about enemies earlier, so that's items that must never be delivered in the same list. And there's also friends, so they're items that must always be delivered together because they've got context. Say, item 2 refers to your answer in item 1, for example. So in the dynamic rules, we've taken a fairly sort of brute force approach where we generate a list of items and then have a look to see whether the friends and enemies have been met. So are there any pairs of enemies? Are all the friends there? If they're not, try again and then just keep trying until you've successfully generated a list that does contain the right friends and enemies, which works as long as your rules, your friends and enemies aren't too complex, but you can run into problems if you have large numbers of enemies and constraints that try to put enemies together or keep friends apart. So in the External Optimiser, we build those friend-enemy relationships in from the start. So they go in as constraints. And if you've got relationships that are just impossible to meet it will work that out straight away. It'll try once. It won't just keep trying and trying and trying, you know, essentially banging its head against a brick wall. It will just say straight away, you can't do it. So, just bear with me, we're getting a little bit mathematical here, so that might not be very interesting to some people, but just a brief talk about how we actually do the linear optimization. So this is an example of a bank of items, really small for a vet exam. Not real, just one I made up. So it's got 9 items, 3 items, we've got 2 different, what we'll call domains, so in Surpass language, they're tags. So we've got an animal tag and a topic tag. And then of the animals, we've got 3 items for the pig, 3 for cow, 3 for sheep, and we've also got topic, so diagnostics and treatment. So when we come to coming up with these equations, these on the right are the constraints. So first thing we need to do is define our variables. So we've come up with a variable for each item, A1 to A9, just use subscript notation there. And each of those variables can have 2 possible values in the solution. 0, which means the item isn't used, or 1, which means it is. And then we can go through, take the wordy constraint and turn them into inequalities, like we've got on the right. So the first constraint is we need 2 items for each animal. So simple mathematical representation of that is take each of the variables for the pig items, A1, A2, A3. The sum of those must be greater than or equal to 2. Because if you've got only 1 pig item, say A1, but not A2 and A3, A1 would be 1, the other 2 would be 0, and the sum of those would be 1. We've not met our constraint. So we do the same for the other 2 animals. So second one is for cow, third one is for sheep. Both cases greater than or equal to 2. Then we've also got constraints on the topic. So the requirement is there must be at least 3 items from each topic. So we define an inequality for diagnostic. First one, just pick the items that are diagnostic. You can see 1, 4, 5, 7. And then the same thing for treatment. And then the final constraint is just the total number of items. So we said here we want a test of 7 items. So we just add up every single variable, because that's just which items are used. That must equal 7. So now, I mentioned the TIFF earlier. This is an example of a TIFF. So I didn't put any of the psychometric values on those items because they're not really very interesting. They're just numbers between 0 and 1. But those represent on each item an item information function. So that's the item equivalent of this. So this is the information function for the whole of the test. But each item has a function a bit like this. So this is telling us theta along the x-axis is candidate ability, and then the y-axis is how much information there is in the test. So it tells us that at -4, which is the lowest ability candidate, up to 4, which is the highest ability, at the highest and lowest abilities, it's not going to tell us much. Whereas in the middle, where it peaks, it's going to tell us more about how good the candidate is, if they're in that range. So psychometricians would come up with the desired target TIFF, and then that consists of a series of values which represent the middle line, and then we're saying our tolerance on that is, in this example, I think I said ±1. So you can see the top line and the bottom line are the upper and lower bounds that we allow for that. So at each point where there's a value, we have an upper and lower constraint. So I think across here in the real test, which I'm going to show in a minute, there are 41 different values at which the TIFF is defined, or 41 values of theta. So that comes out at 82 constraints. So we've not talked about what we're actually optimizing here, because everything is all about just making a test that's good enough rather than making something that's the best. But as we talked about earlier, we're generating multiple lists. There isn't a best form, or there might be a best form, but we're not interested in finding that because all the others, by definition, are not good. We want lots of lists that are all within the acceptable range of quality. So the thing we're going to try to optimize is the exposure of the items instead. So this is an optimization function. It's just all of the variables, each of which has its own coefficient, which we call C1 to C9. The first time we do it, we haven't got any exposure. They've all got an exposure of 0. So we just generate a random number. It can be, in a range between 0 and 1, say. And then we say, and we're going to minimize that. So all that's going to do is generate one of the possible solutions that meets all of the content constraints. So every time we're doing this, whatever we're optimizing, we're always applying those content constraints and psychometric constraints in the same way. But we're just ensuring we get a different list each time. So the first time, we get set items. Then for the second iteration, we're going to feed the exposure back into those coefficients. So we change these coefficients for the items that have been used so that they increase slightly, which means those items are therefore slightly less likely to be picked. We run it again, feed them back in, run it again, and you just keep doing that. And you'll find that if an item is being exposed a lot, it might be because it's just better at meeting the psychometric targets. Or, it's possible that you've said I need 10 items from domain 1 and there are only 11 items in there. Well, those items are going to be exposed fairly highly, but it will at least try to minimize their exposure. And then another sort of key aspect that we built into the product was that just as a part of getting trust in it, we need to be able to show what lists will be generated before they're generated. So if you're just running this, you'll set your bank, put your items in, and just schedule your tests, and it will just generate lists based on this. But if you have never used it before, you might not trust it. You can do, but it's up to you. So what we decided is have a way of being able to generate lists in a simulation, just effectively in the lab, and then we could give those lists to psychometricians or whoever it is that wants to analyse them, just to check that they are acceptable and all within the bounds and the overlap's not too high, not got too high exposure. If they are acceptable, we take those random numbers that were generated in the lab, put those back into the application, and they are the starting point for the live item lists that will be generated. And then we know that those lists that were analysed will exactly match the lists that are generated by the system. So we'll just have a look at an example. So this is actually the same bank that Leanne talked about in her slides, but those of you that look carefully at the figures will see they're not exactly the same, and that's because it wasn't the same simulation. So it was the same items, same constraints, but I generated 1,000 lists separately. So the stats are similar, but slightly different, obviously, because they will be different. It wasn't the same run. So just under 1,600 items, 53 content constraints. The target TIFF was defined at 41 different values of theta, so that's 82 constraints, obviously top and bottom. 537 pairs of enemies. I think that's slightly different from what Leanne said. I don't know whether I counted mine slightly differently, but it was the same set of rules anyway. And then the requirement was for 150 items per list, which in total comes to 727 linear optimizer constraints, which is quite a lot. And as you can see, it's the enemies that are the sort of the main constraint or the main problem. So not having enemies does greatly simplify it and speed it up, but they're unavoidable. So that's just one thing you have to have. But one key point here is that enemies and friends, there aren't actually any friends in here, are defined at item level rather than test level. So if you create your bank and your items, you decide what their enemies are. Those enemy relationships will be maintained across all test forms. They don't have to be defined at form level. So it's just the content constraints which are specific to the test and the psychometric constraints that need to be defined per test. And then this is, again, a different way of showing the kind of data that Leanne was looking at earlier. So this is our exposure. So we generated 100 lists, and then you can see the exposure of the items. So it was 150 items from 1,600, a bank of 1,600. So the average exposure is just under 10%. That is just what it is. And you can see that by far the highest level of exposure is between 10 and 15%. So we've got quite a good grouping of exposure. And then there's just, I don't know if how good your eyesight is, but there is just one little line there in the 15 to 20 range, but that's only a few items, and then nothing higher than that. And then it also tails off quite quickly as you get to lower exposure. So there are very few items that have very low exposure, which again is good because there are costs associated with creating your items. So if you're going to pay for them to be made, you want them to be used in your tests. And then the final bit of data in the analysis is the overlap. So the average across all of the forms, so taking every possible pair of generated lists, was 10%. And then the maximum across the whole of the 1,000 forms was 57, which is 38%. But again, that's the more lists you generate, the higher that value is going to be, because eventually you will come across a pair that are identical, but that's unavoidable. Yeah, I mean, that's 10%, I think, is an acceptable value. So I know I've skipped over some of the detail of the psychometric stuff and the linear optimizer things, but I'm available later on if anybody wants a more in-depth discussion. We can go into a bit more detail about it.